Hi students, this is Srinivas. Today's class we discuss type and order. Here type and order of the system. Here the type and order of the system. Here consider a closed loop system. Here for this is the closed loop system. For this closed loop system is the gain is g of s. Here the C of S is the response. Here the R of S is the input. Here the plus or minus. Here the feedback path. Here the H of S. Okay na? This is the closed loop system. Here the E of S is the error signal. Okay na? For this closed loop system, we find the transfer function. Here the C of S by R of S is equal to C of S by R of S is equal to here G of S by 1 plus G of S into H of S. This is the we know the transfer function for the closed loop system. Okay na? By using this closed loop system, here today we discuss what is the mean by type, what is the mean by order. Here this is the transfer function is the C of S by R of S. Here in terms of, please remember one thing, in a transfer function denominator is always consist of poles. Here in numerator it consists of zeros. Here in terms of poles and zeros, here the C of S by R of S is equal to, here the K is, let's assume, constant. Here the S plus Z1, S plus Z2, S plus Z3 by here the S power n. Here the S plus P1, S plus P2, S plus P3. Okay na? In this function, in this transfer function, here the S plus Z1, S plus Z2, S plus Z3. These are the zeros. These are the zeros. Next one is these are the poles. In denominator, it consists of poles. Here, let's consider this transfer function. It consists of 3 zeros and 3 poles. 3 zeros and 3 poles. This is the S. Okay na? This is also one pole. Here the N is nothing but it is the order or degree of the system. Here the K is the constant. K is the constant. Based on this function, based on this transfer function, we define what is the mean by pole, what is the mean by type, what is the mean by order. How can you estimate the type and order? Today we will see. Here in this equation, if the n is equal to 0, if the n is equal to 0, here the S power is 0. Here the S power is 0 is nothing but there is no poles located on origin. Okay na? There is no poles located at origin. Here the type is nothing but the number of poles. Here the number of poles located at origin. Okay na? Here the type is nothing but here the number of poles located at origin. Based on poles we define the type. What is the mean by order? Order is nothing but highest degree of denominator. Highest degree of denominator. Here in this transfer function, if S is equal to 0, if the S is equal to 0, there is no poles located on origin. This is the xy plane or real axis and imaginary axis. If the S is equal to 0, there is no poles located at origin. Okay na? If in case here the n is equal to 1. In case n is equal to 1, here the n is equal to 1 is nothing but here the one poles located at origin. Here this is the one pole located at origin. Here the one pole located at origin is nothing but here the type is nothing but the number of poles located at origin. Okay na? How many poles are located at origin? Only one pole. Is nothing but the type of system is the type 1 system. Type 1 system. Okay na? Type 1 system. Here next these are the 3 poles. Okay na? Here the multiply these 3 poles. Here the S square, S cube, S power 4. Okay na? Here the highest degree is the 4. Highest degree is 4 is nothing but the order of the system is the 4. Here the n is equal to 1. Here the type 1 order is 4. Order 4. Okay na? In case if n is equal to 2, Here n is equal to 2 is nothing but how many poles located at origin? 2 poles are located at origin. Here the 2 poles located at origin is nothing but here the system is type 2. Here the type 2 system. Okay, here the number of poles located at origin is the 2. Okay, multiply these 3 poles. Here the s square, s cube, s power 4, s power 5 is nothing but highest degree, and the highest degree is the 5 is nothing but order of the system is 5. Order of the system is 5. In case here the number of poles are increases at the origin, here the number of poles increases at the origin, that is indicate the type of the system. Highest degree of the denominator is indicate the order of the system. Okay na? Here by conclude that here the pole type is nothing but the number of poles located at origin. Order is nothing but highest degree of the denominator is called order of the system. Okay na? This is the type and order of the system. We discuss steady state error. Here we derive the steady state error for the closed loop system. Here this is the closed loop system. For this closed loop system, we know the gain G of S, the response is C of S. Here the feedback path is H of S. Okay na? If for this closed loop system, here the elimination of negative feedback R of S is the input and the E of S is the error signal. Okay na? For this closed loop system, we find the response and the error signal E of S and the feedback path H of S. Here, see here, by using this closed loop system, the response C of S is nothing but here the E of S into G of S. This is the forward gain. This is the forward gain. Next one is the here the C of S and H of S is the feedback path. Here the C of S into H of S is the feedback path. Here by using this diagram, here the E of S is error signal. E of S is error signal. Here the C of S is response, is nothing but output. Is nothing but output. Here the H of S is the feedback. H of S is the feedback path. Next is the R of S is input signal. R of S is input signal. Okay na? By using this diagram, here the E of S, here the E of S is equal, here the E of S is equal, here the R of S minus, here the C of S into H of S. By using this diagram, this is the equation number 1. Here the E of S is equal to R of S minus elimination of negative feedback, here the C of S into H of S. Next one is the response is nothing but output C of S is equal to here the E of S into here the G of S. Equation number 2. Okay na? By using these two equation 2 substitute in equation number 1. Okay na? We will get here the E of S is equal to here the R of S, okay na, minus here the C of S is nothing but E of S into H of S into G of S. Okay na? By using this equation, here the E of S shifted to this side, here the E of S plus E of S, G of S, H of S equal to R of S. Okay na? By using this equation, here the E of S common is the E of S into 1 plus G of S into H of S, okay na, equal to R of S. So we need to find the error signal constant or the steady state error. Here the steady state error, here the E of S is equal, here the R of S by 1 plus G of S into H of S. This is the steady state error for a closed loop system. Okay na? Here steady state error E of S is equal to R of S by 1 plus G of S into H of S. For this equation, here the apply the universal Laplace or convert it into time domain. Here the E of S is equal to universal Laplace E of S. Okay, na? Is nothing but here the E of t. Or shall we write here the inverse Laplace E of S equal to E of t. This is the time domain specification. This is the time domain specification. Here the steady state error constant is the ESS. Steady state error constant is the ESS. It tends to value of t changes here the t to infinity. T to infinity. Here the steady state error ESS is equal to limit s tends to t tends to infinity. Here the E of t. E of t. Here by using the steady state error ESS is equal to limit tends to t tends to infinity E of t. We find the by applying the final value theorem and apply the Laplace equation. Here the steady state error, we will get the steady state error. Here the ESS is equal to limit t tends to infinity. Here the s into f of s. S into f of s. By applying the final value theorem, limit t tends to infinity. F of t is equal to limit t tends to infinity s into f of s. This is the final value theorem. By using the final value theorem and Laplace, the steady state error ESS is equal to limit t tends to infinity s into f of s. Here the steady state error f of s is nothing but E of s. Here the ESS is equal to limit t tends to infinity s into, here the steady state error constant is the R of s by 1 plus here the g of s into h of s. This is the final value of steady state error constant. Here the ESS is equal to limit t tends to infinity s into R of s by 1 plus g of s into h of s. By using this steady state error equation or the steady state error, we test the different types of systems. Okay, na? Type 1 or type 0 and type 2, type 3, whatever may be. Okay, na? Here the steady state error ESS is equal to limit t tends to infinity s into R of s by 1 plus g of s into h of s. Okay, na? Next one.